Hello students, welcome in the part 8 of D and F block elements. So we were discussing about the melting and boiling point of transition elements. Before I proceed further, let me ask you, do you know the formula of coconut water? Or do you know how to make it? How coconut water can be made? Think. Only a chemist can tell you. Okay, here it is, your coconut water, and here this person is telling you how you can make coconut water. CO, 2 times of CO, then half of nitrogen, that is only N, then UU in the presence of UUT, water. So here you can know what is the formula of the coconut water and how can you prepare. Okay, let us proceed further. Let us continue. So we were discussing about the melting and boiling point of transition metals. Now in 3D series, in next we will see in 3D series, that is साइंस टीचर वेरिक रूल मांगे फेयर कॉपी निकालते क्यों नहीं जनाब. In 3D series, if you see scandium to chromium, melting point and boiling point increases, and then manganese to zinc decreases. Then thereafter you will see decrease in the and that can be made clear from the graph. Here somewhere will be scandium. So scandium to chromium increase, then manganese, and then further it is you will see up to zinc, it will decrease. Similarly everywhere in another series you will find the same trend. So in 3D series, scandium to chromium melting point increases, and then further manganese to zinc decreases. Okay, as the number of why, what is the reason for that? So the reason is there, as the number of electron in D subcell increases, as the number of electron in D subcell increases, you will see what the bonding the covalent bonding, and in fact the metallic bonding too, the covalent bonding becomes stronger. The covalent bonding becomes stronger because the more and more electron will participate in that and make this bond stronger. And this trend, if you see, this trend is up to chromium, molybdenum and tungsten group. So up to these elements, number of electron in valence cell in the D subcell increases, and that's why they are having highest unpaired electron electron in d subcell. Of course, manganese is having manganese and other member of that having more than that, but up to chromium and molybdenum and tungsten, you will see all the electrons in d subcell, they will participate here. All the electrons in the d subcell, they will participate in making covalent bond. So in fact, I must say there all the electron in the d subcell not highest, because in 3D series you can say manganese is having highest unpaired electron. So I should say all the unpaired electron in the d subcell, all the unpaired electron in d subcell, they participate in making covalent bond. It means here the covalent bond become strongest, and that's why in the middle these three are having highest melting point. And this is apparent, apparent from this diagram, clear from this diagram. We will see chromium, manganese and tungsten. Okay, now what is wrong with manganese? Exactly half-filled electronic configuration d5, and that electron configuration is definitely going to affect that. So we'll see here what happens in manganese and technetium. You'll see manganese and technetium have comparatively low melting point due to weak metallic bonding, because of I must say stable, exactly half filled or stable half filled d subcell. Now this is apparent from the diagram. If you see the trend in the, here it is manganese, here it is manganese, the trend in the enthalpy of atomization. So here the atomization enthalpy of manganese is also low, because the completely exactly half filled d5 electronic configuration. Here manganese, same in the next series you can say technetium. Okay, so manganese here and technetium both contain d5 electronic configuration, and that's why their atomization enthalpy is low, and their metallic bonding become somewhat weaker, and that's why their melting point is also becomes low in the middle. Okay, so this is about their melting and boiling points. We'll continue that in the next video. Bye.